Hey guys, today we're starting chapter 8, which is all about sequences, series, and summations. So I know we just finished up chapter 6, and now we're just starting chapter 8, which tells you we are just going to skip right over chapter 7 this year. So it is something that there's a couple of different skills that, show back up in some pre-calc stuff and in, senior math and things, but it's topics that are not as fundamental or necessary moving forward, where sequences and series are something that do have some other applications to them. So we're going to dabble a little bit here in this chapter, and then move on to chapter 9 for our last couple of things before our final. So for 8.1, I did split this up into 2 days. The first day just reviewing what we know about sequences, what we learned in Algebra 1 about sequences. And then tomorrow, day 2, we'll jump into what it means for us to change this sequence into a series and kind of how that works. And then we'll get specific into arithmetic and geometric sequences and series, as well as some other types of series as well. So here in box 1 for 8.1 day 1, we're just kind of going back through what it means to be a sequence. Remember, a sequence, that's just an ordered list of numbers. It's just a list of our outputs. We have values in that list, and we call those terms. So when we're looking at kind of how we classify things in our traditional method, the term or the position number, so where it is in the list, is my domain, right? That's the n value that we will use for our equation. And all of those get mapped to different terms in my sequence. So here our range is made up of the actual terms in our list, and that's always denoted by a sub n. So a sub n just meaning that term in the nth position. So our first term in the list, a sub 1, has a n value of 1. It's in position number 1. Our 15th term in the list would be a sub 15. That would be our 15th term in the list. Its domain is n. Its n value is 15. Its output is a sub 15. So that's just, again, how we'll use those. And obviously then here we would have comma in between separating out my list, whether we have those dots there or not. But that is what my sequence is made of. What we actually see in the sequence are my outputs. Those are my y values from that sequence. And then the position that they are in is the domain. We have 2 different types of sequences, just on their classification, not necessarily in the pattern within those sequences. We'll obviously talk about the different types of sequences and the way that they grow, but we do have a difference between whether a sequence or a series stops or it continues indefinitely. And of course, we just use the words finite versus infinite to mean those 2 different things. So if we have a sequence that stops, it has a last value in that list, we call that a finite sequence because it does not continue on forever and ever. Our infinite sequence has those very important 3 dots at the end, meaning that it continues indefinitely. My domain is going to continue going further to the right. I'll continue having terms further through my list. So to start with, we're just going to work on being able to write out the terms of my sequence. So we can be given our equation in a couple of different ways. This is standard sequence notation, a sub n sequence notation. If we're just looking for the first 6 numbers in that sequence, we have a couple of different ways of doing that. If we're looking for the first number in our sequence, that would mean it would have an n value of 1. So if I wanted to find the first number of my sequence, which would be a sub 1, I would just plug in 1 for n. So 2 times 1 is 2, plus 5 gives me 7. That tells me the first number in my sequence is 7. Now you could continue through and just plug in 1 through 6 into your equation to be able to figure that out, but hopefully we still recognize what our different types of equations look like, and it will be something we continue to kind of reinforce as we move forward. But this is a linear equation, right, which means it's an arithmetic sequence. Here we should notice that 2 attached to that n means that we're just growing by 2 each step of the way. So like if I plugged in 2 here, I would get 2 times 2 is 4, plus 5 is 9, and that just confirms that we're growing by 2. So rather than plugging them in every single time, use 1 to find your first value if you can't just identify it right away, and then just continue your pattern. They're looking for the first 6 terms of the sequence, so 7, 9, 11, 13, 15, what's that, 1, 2, 3, 4, 5, 17, and that's all I need to do. So those are my first 6 numbers in that sequence, all the odd numbers up to 17. Another way that they can give us the equation here is in function notation. So in function notation, they're just replacing a sub n with f of n. It still means the same thing. N is still my term number, my position number, and then f of n would be what the actual term is in that position. So here, if I want to know what the first number in that sequence is, f of 1 would be 1 times negative 3 to the 1 minus 1 power, which is, I'll go vertical here, 1 times negative 3 to the 0, which negative 3 to the 0 is still just 1, times 1 is positive 1. So I know that the first number in my sequence is positive 1. Now, again, hopefully we get to the point where we start recognizing patterns. This is definitely my exponential equation, right? The chapter we just finished up, chapter 6, was exponential and logarithms. This is definitely an exponential equation, which means it's a geometric sequence, which again we'll talk about in 8.3, I think it is. But in a geometric sequence, in a exponential equation, this was always my a value, right, which was my starting value, and then this number here, which was my base, is my multiplier. So again, if you don't feel like just continuously plugging in 1 through 6 into your equation for n to find the different terms, I can use this kind of as a shortcut where I know that my first value is 1, that's what we plugged in for, or alternatively, you could look in your equation and say, oh, hey, look, that first thing right there in front, that's a positive 1. That's my first number. That's my starting value. So then from here, I'm just multiplying by 3 to get to my next term in the sequence. So 1 times negative 3 is negative 3, times negative 3 is 9, negative 27, positive 81, and negative 243. Those are the first 6 terms in that sequence. So that's just writing your terms. Again, you're just if nothing else, you can always just plug in your n values from 1 through 6 and get what you need. Now, getting to boxes 3 and 4, we're going the other direction. We're going to be finding and writing our rule given a sequence to us. So they're going to give us the sequence. We have to work backwards to be able to figure out what that sequence's equation would have to be. So there's, again, a couple of different ways of going about this. I like to try and focus in on what type of sequence it is and identifying that pattern first. So this one, if we look to see kind of how my numbers grow, I'm going from 2 to 5, which is adding 3, to 8, to 11, 14, so on and so forth. So we can see each step of the way I'm just adding 3 to my sequence. So since we're adding or subtracting, that was always my arithmetic sequence. And the equation for that, which again we'll review in 8.2, was dn plus a sub 0, where d is your common difference, and a sub 0, that's the number before the list starts. So like 2 is my first number in the sequence. Whatever would have to come right before my 2, that's a sub 0. D is my common difference. We already identified that as being positive 3. So really all I'm looking for is what that unknown thing is that would have to come before my list. So if I was taking something and I had to add 3 to it to get positive 2, well, that something would have to be negative 1. Right? Negative 1 plus 3 is positive 2. So that tells me my a sub 0 value is negative 1. So if I put those two things together, a sub n equals My common difference was 3, and then negative 1 was my a sub 0 value. So that's my equation. Okay, taking a look at number 4. Number 4, identifying my pattern first. From 4 to 16, well, I could say that that's adding 12, but looking at 16 to 64, I know that's not going to fit either. So what I should see here is that each step of the way, not plus, we're multiplying 4. 64 times 4 is 256. 256 divided or times 4 is 1024. So in this one should be more familiar to us, or at least more recent for us. This is a geometric sequence, which is exponential. That equation is a sub n equals a sub 1 times r to the n minus 1 power, where a sub 1 is my first term, and then r is your common ratio, which, again, we always identify as that multiplier. So whatever I had to multiply by to get from one to the next, that's my r. Whatever that first term of the sequence was, that's my a sub 1. Exponentials, these geometric ones, far easier at your equation because everything comes directly from your sequence. All right, so here we'd have a sub n equals, my first term was 4, my multiplier is 4 to the n minus 1 power. And that's it for number 4. So those ones, again, these next two sections we'll go through, we'll go through 8.1 day 2 first and talk about what a series is versus a sequence, what those differences are. Spoiler alert, it's just changing the commas into addition signs. We're just adding them together instead of making it a list. But then after that, 8.2 is arithmetic sequences, 8.3 is geometric sequences. So we'll kind of do a deeper dive into each of these. Box 4 is some weird patterns. They called it crazy patterns up here in the title of this box. But it's just looking at things a different way. It doesn't necessarily follow an arithmetic pattern, a geometric pattern. Sometimes it's a combination of them. Sometimes it's totally different. And you have to do some kind of next level thinking to try and figure out what that pattern is. But I always find it helpful. So when we're looking at these sequences, and look at number 5, we've got 1/2, 2/3, 3/4, 4/5, and 5/6. Now, a lot of us probably recognize 1, 2, 3, 4, 5 up top, 2, 3, 4, 5, 6 in the bottom. But trying to figure out what I would do to get from one to the next in my sequence might still be a little bit confusing to us. What I always like to do, what I find helpful when I can't figure it out, I write out what my n values are to try and figure out what equation I could write in order to give me my terms. Because I know that my equation has to use n, so that means I have to be able to use these numbers to get, what my term is in the actual position of my sequence. So if I have to use 1 to get 1 over 2, 2 to get 2 over 3, 3 to get 3 over 4, 4 to get 4 over 5, 5 to get 5 over 6, the top row becomes really easy because my sequence, the top row, is just what position number I'm in, right? Position 1 was a 1 up top. Position 2 was a 2 up top. 1, 2, 3, 4, 5. It just matches the position number. And my denominator becomes easier now, too, because it's just 1 bigger than that. So it's just n plus 1, right? So if I'm looking for my first term, 1 over 1 plus 1, 2, 1/2. If I'm looking for the fifth term, n is 5. 5 plus 1 in the bottom, 5 over 6. That would be my pattern. So a little bit different just in the way that it is written, but not too bad. 6, a little trickier, because, again, looking at this, most of us will probably be able to see that my numerator is even, my denominator are my odds, but being able to write an equation, again, that utilizes my n value of 1, my n value of 2, my n of 3, my n of 4, might still be a little tricky for us. So we already saw one equation, like one pattern that we were given today that gave us just an evens or an odds. If you remember and look back to Number 1, that very first one, 2n plus 5, gave us just odd numbers as my output. And the reason that happened is because when you multiply by 2 on your n term, you're either going to be given an even or an odd, depending on what else is going on in your equation. So if I wanted just the even numbers, if we're looking at number 6 here, if I wanted just the even numbers, and I had to use n, the way to get an even number is just multiply by 2. Right? That's always going to give you an even number. 2 times 1 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, 2n gives me that output up top. So I'm good with that. Underneath is a little trickier because we want to try and plug in 1 in there and get a 5 back out. I want to get a 2 in there and get a 7 back out. So 2n, usually 2n plus 1 or 2n minus 1 are the way to get the even numbers, kind of as just a general generator to get the odd numbers. But here that doesn't work, because if I plug in an n value of 1, 2 times 1 is 2, plus 1 is 3. And I want 5 instead. So if I had 2n in there, 2 times 1 is 2, I would have to add 3 to give me 5. So we want to check now, if that's the one that fits for my first one, we want to check to see if that works for others. So if I plugged in, I'm going to check this last term that's given to me. If I plugged in 4 in there, I should get 8 over 11. So 4 times 2 is 8. I'm good up top. 2 times 4 is 8, plus 3 is 11. So I'm good. That works. That's my pattern. A sub n equals 2n over 2n plus 3. And that's my pattern. So that's sequences. That's all I have for you for today. Tomorrow we will do a deeper dive into what we call series, which again I kind of already previewed for you what that looks like. Very similar to sequences, kind of the same ideas of how numbers grow from one to the next in my sequence, or how in this case it'll be a series where we're taking and adding up terms of a sequence. Spoiler. But that's all I have for today. So homework is right up there on the board, well, screen, whatever. Page 414, 6 through 26, just the evens. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.